Hello guys, welcome to the remainder of our lecture that kind of goes along with density and how temperature and salinity affect density. So yesterday we learned that as the salinity of water increases, our density will also increase. So I could ask you, if I gave you different containers of salt water and told you that one had like 3 moles of salt and the other one had only a half a mole of salt, you should be able to predict for me which one had the higher density based on salinity. So if I told you that salinity and density had a direct relationship, you should have been able to tell me then that the cup with the 3 moles of salt in it is denser water than the cup with just a half a mole of water. And we also kind of talked about density again, just to cover our bases. So here we're kind of talking about relative density. So we're not actually finding the density of the salt water. It's just what is more dense and less dense than something else. So we call that qualitative. It's not very quantitative. There are no numbers for this. It's just something that we can kind of observe and describe. Like if I have a pool, say, and I am playing water basketball, if I drop the basketball onto the water, it's going to float. And if an object floats on water, then we can say that it is less dense than water because it's floating. And in the same way, if I drop my pool goggles as well if I drop my pool goggles and they float, or they sink, then I can tell you comparatively that the goggles have a higher density than the water because the goggles sunk to the bottom. The example we used in our density notes was if I had a cup of water and then I put some styrofoam pieces and a rock in it, the rock is more dense than water because it sinks, and the styrofoam is less dense because it floats. We are going to, so part of this, what you're watching right now, is the rest of our lecture, our video, our actual notes. But I had my 8th graders in the morning yesterday do the temperature lab that those in class are going to be doing today. So with the temperature lab, and I didn't get to say it too much in the lecture, but if you have the supplies to do the temperature lab, which would be food coloring and a clear glass and some way to make red water hot and blue water cold, and you didn't even need to stick with those colors, they just need to be 2 different colors, and then you need room temperature water. That's all you need. We use pipettes, but you could do this even if you just took a straw. You know how if you stick a straw down in a glass and you put your finger over it, it holds the water. You could just pipette it in that way. That's kind of the same thing. So you could really recreate this experiment, but if that's not something that you'd like to do or you don't have access to, you're more than welcome to just watch the video and use those results to fill out your lab sheets. But anyways, so this is the remainder of our temperature lecture. We've already done all of this. So here's our notes on temperature. So sunlight heats the surface of the ocean water, H2O. That's kind of, I would say common knowledge, but maybe if you've never been swimming in a lake or a pond, you might not know this. But if you have been swimming in a lake or a pond, I want you to close your eyes for a second and remember what it feels like if you swim deep down into the very bottom. Say you've dropped something and you're trying to find, or you're just trying to find the bottom of the lake or pond that you're in. As you travel down, 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 you're actually going to experience colder water. Part of the reason is because the sunlight is actually heating up the surface of the water. In our oceans, we have what we call 3 temperature zones. And the first one is the warmest. We call it the surface zone. It's about, so where the sea meets the air, to about 300 meters down. Sunlight only penetrates a few meters, but the wind and waves mix the heat evenly through the surface zone. So, and you have a little chart on your notes. You can see temperature is actually, so here, looking at your notes right here. So you've got the 3 different layers right here, and you've got a graph that as you go down, it's temperature, or as you travel from the top of the paper to the bottom of the paper, you're increasing in depth. And as you're traveling from the, let's see, what is this, the left of the paper to the right of the paper, your temperature is increasing. So if you can see that little white line, it's tracking it. So as the temperature, or as you get deeper and deeper and deeper, your temperature is actually going down. And that's what it says. That's what we would expect based on the information here and what we have observed in our own lives. So again, the sunlight doesn't go all the way down to 300 meters. It only penetrates a few meters down, but because we have the ocean as a churning being, it's not steady. That wind and the wave mix the heat evenly through the surface zone. The next zone that we come to, so between 300 meters and 800 meters below sea level, is what we call the thermocline zone. It's marked by a rapid temperature change with depth. So this marks the boundary change between the surface zone, which is pretty warm, and the deep zone, which is very cold. And the deeper you get in the deep zone, in a second we're going to talk about, the colder it gets slowly. But this thermocline, thermo means heat, cline means change. So we have a temperature change right there. So for the most part, in the surface level, we're pretty evenly warm throughout. But the thermocline, you can see that in our graphic, quickly decreases, and we have a very big change as we go deeper down into the ocean. And then, of course, the deep zone, the temperature continues to decrease, but only slowly, and it's 800 meters to wherever the ocean floor is. So with this, you're going to see, if we were to travel ourselves through the different zones of the ocean, you're going to see all kinds of different life down there. So you'll see in the warm surface zone all those colorful fish, but as you get deeper and deeper down, they start to lose their color a little bit, and we don't see that many photosynthetic organisms in the deep zone because there's no light to help them photosynthesize or make their own food. So really and truly, the deep zone is almost devoid of plants or photosynthetic plankton. But there are a few exceptions, as always. Okay, so we've already done these notes. These are your salinity notes, so I'm going to zip right past through here, and we're going to finish talking about ocean acidification. Okay, so here we are. Ocean acidification. This is when the excess carbon dioxide from the atmosphere makes it into the ocean's waves. I told you before in the previous lecture that where the boundary between the ocean meets the air, we're actually getting an active change and exchange of molecules. So the carbon dioxide molecules are entering into the ocean, and then it'll actually become carbonic acid once it hits with the water. So once the carbon dioxide hits the water, it becomes carbonic acid, and that makes the acidity of the ocean water increase. Okay, so our second bullet point says CO2 increases the acidity of the water. That's because the CO2 combines with some molecules in the water, forming carbonic acid. It's a different chemical. Acid indicates acidity, and it is very detrimental to ocean organisms, specifically ones that make their shells. So calcium carbonate, CO3, is an ingredient that mollusk is the only word that's coming to mind, but there are more organisms that have this in there, but think like seashells and mussels and oysters. So they are actually suffering pretty badly because of this increased acidity. 25% since before the Industrial Revolution, greater than any time in the last 2 million years. I'm not exactly sure what 25%. Maybe we have increased in acidity 25%, but I'm not exactly sure. So I apologize for that one there. But the decreased carbonate availability and increased acidity really hurts these animals. So what they're doing is, instead of having a nice hard outer shell, they have a very soft shell, which is easy for predators to get in and hurt themselves. Easier for predators to get them and eat them, but it is bad for the organism itself and bad for fishing industries. So fishing industries as well. Just so you know, here's our pH scale, and we're going to study this more when we study the weather systems, but these are acids down here, these are bases, both scales. The closer you get to 14 and the closer you get to 0, the worse it is for an organism. Here is an example of how much, sorry, there's someone at the door. I'm trying to decide if I should open it. So here we are. This is 1960s probably. We've seen a definite increase. So carbon dioxide always varies in the atmosphere. That's what this is. And we've seen a definite increase as we go closer and closer to modern times, and it's only extended since then. But what we see is as this rise in atmospheric carbon dioxide happens, we see a decrease in the pH of the salt water, which is not good for animals that make cells or make shells. So here's an example. Bad for fisheries. We'll talk more about this. I'm trying to decide if I should open the door. So there's a pretty negative impact of this pH increase on our ocean. And ocean definitely, but if you don't care for the little ocean critters, it also is pretty detrimental to the impacts on fisheries. So we experience economic losses if we don't have things for like if we don't have oysters or scallops. We don't get the money from that, and they are pretty expensive things. We're not getting a lot of oysters or scallops, we've got to fire people, so we don't have any jobs, which disruption of livelihoods. That's what that stands for. That's what that signifies. So if we don't have enough oysters to get, then I'm going to have to start firing people, because if I don't even make enough to provide for me, I can't provide for you too. So it kind of changes everything. And just so you know, global shellfish production is about a $10.5 billion industry here in the U.S. So we would experience, and we are experiencing, significant economic losses due to this change in the pH of our ocean water. Okay, this is our lab. This is what we're going to do. So this is a separate thing. For Canvas today, you'll go over to your lab, make sure you do the lab sheet as well as finishing these notes. Have a great day, guys. Email me with questions.